Welcome to today's video where we're walking through question 15 of the Spring 2019 MAS1 exam. You are given the following information. X subscript 1, X subscript 2, X subscript 500 is a random sample of 500 claims. The distribution function is f of x equals 1 minus parentheses 200 over x and parentheses to the power of alpha for x greater than or equal to 200 and alpha greater than or equal to 0. The summation of x subscript I from 1 to 500 is equal to 117,378,845, and the summation of the natural log of subscript xi's from I equal 1 to 500 equals 3,646. The parameter alpha is estimated using the method of maximum likelihood. Calculate the estimated probability that a claim will exceed 400. In this problem, just need to know two things: taking derivatives, as with almost every other problem on this exam, and then secondly, what the maximum likelihood methodology is and how to do it. So if you prefer reading to hearing me talk, feel free to pause and read the explanation. But just to walk through this, we have some data, so that's all those xi's. We want to know, for here I have alpha, because that's what we're using in this problem, but it could be any hyperparameters. Given a hyperparameter value, what is then the probability of seeing the data that we saw? So we can write this as the product, because they're independent random samples, and they all have the same distribution PDF f. So what is the probability of seeing x1 given some selection of alpha using that probability density function, and then we multiply them all together. If you're not familiar, this capital pi just means product. So in the same way, eventually we're going to look at a summation. It's the exact same thing, but instead of adding all the different values, you're just multiplying them all together. So that's what this denotes. So we know that the probability of seeing the data that we have given some hyperparameter alpha is equivalent to just the product of all those PDF values of all those different x's with that assumed alpha. Now what we can do is just take the natural log of this, and the reason we're going to do this is when we need to take a derivative, it makes our life way easier. Derivatives just become really simple. Now the reason we can do this is because the natural log, let me take a step back. What we're trying to do is, what selection of alpha maximizes the probability of the data? So that x value, or that alpha level, which one produces the maximum probability? We don't actually care what that probability is, right? We just care about what alpha is. And so if you were to, say, take this function and multiply it by some constant, let's say we just multiply it by 10, if you were then to take the derivative and find the maximum, you would still get the same alpha level is maximizing that function. It would just, the resulting value would be different, but you don't care. And that's why, similar to multiplying by a constant, we can take the natural log, because it's a monotonic transformation. So that's why we can do it, and again, the reason we're doing this is to make the derivatives a lot simpler. And so what we can do is, okay, I'm going to take the natural log of this with the end result of us taking its derivative. But what's nice is when you take the natural log of the product of these PDFs, you can break those out. So the natural log of a times b is equal to the natural log of a plus the natural log of b. And so that's why we can break it up here. And now we get to move from the product to our more familiar summation, that's sigma. And so now we can just rewrite all of this as the summation of the natural log of the PDFs from 1 to 500 given some alpha. So this is a version of the probability of the data given some alpha, and then if we want to maximize this, we can just take its derivative with respect to alpha, set it equal to 0, and what alpha maximizes that function. You could take the second derivative to make sure that it's a maximum and not a minimum, but as with most questions for MAS1, normally just taking the first derivative is sufficient. I don't think I've seen a problem yet where they try to trip you up and it's actually a local minima. Now we can move on to the calculations. So first off, just want to remind ourselves of the CDF that we were provided. So that was 1 minus 200 over x to the power of alpha. And then just to make the derivative simpler, I decided to rewrite it, pulling this x out and putting it to the power of negative alpha. So now when we take the derivative to get to the PDF, so we can take that maximum likelihood, the derivative of this is that negative alpha comes out, and then negative alpha times that negative becomes positive, and then subtracting 1 becomes negative alpha minus 1, and that's why when you move x back to the denominator, it's just alpha plus 1. And then finally that 1 just goes away when you take the derivative. So that's how we get that PDF. Next, we'll recall that we care about taking the natural log of our PDF, and so taking the natural log of this and knowing that our the natural log of a times b is equal to the natural log of a plus the natural log of b, we can break these out into different components. So first off, this alpha is here. Next we have the natural log of 200 to the power of alpha. That's another property. So the natural log of a to the power of b is equal to b times the natural log of a. So we're just pulling out that exponent to the front, multiplied by the natural log of 200. And then finally, again, this is just x to the power of negative alpha minus 1. And so again, we can pull out the exponent, so minus alpha plus 1, because it's in parentheses, multiplied by that natural log of x. Again, recalling as we walk through that maximum likelihood that what we want to maximize, so what we're going to take the derivative of, is the summation of the natural log of the PDF. And so writing that out, we get a constant here. This natural log of alpha is going to be the same for all 500 x's. And so we can just pull that out and multiply it by 500 to account for all of them. Likewise, we can do the exact same thing with the second portion. And then finally we have this summation here. So we can pull out the constant alpha plus 1 to the front, the negative times that, and then we're just left with the summation of the natural log of x's. At this point we can take a derivative with respect to alpha, because again we care about which alpha maximizes the likelihood of seeing the data that we're seeing. So taking this derivative with respect to alpha, you get 500 over alpha for this component. This alpha just goes away, so you're left with this constant. And then finally subtract off this natural log of x. And the reason for that is you break this up into its two components, so it's going to be negative alpha times the natural log of x, so the alpha just goes away. And the second component is that 1 times the natural log of x. There are no alphas present, so the derivative is 0. At this point, side note, if you have ever heard the term sufficient statistic, this is what it's referring to. So a sufficient statistic is all the data that you need to track in order to calculate the maximum likelihood. What's the minimum amount of information you need to know that is sufficient to calculate that parameter? And so what you see here is to determine the best alpha when we set this to 0, all we need to know in terms of x's are these 500s, so the number of observations we have, as well as the summation of the natural log of x. And so you can imagine if you were just tracking data by hand, I don't know why you would do that. You wouldn't want to have to write all the x's. Maybe you just in a calculator want to keep summing the natural log of x's, and then at the end of it all you only have one number you have to keep track of, and that's sufficient for calculating your optimal alpha. So side note aside, I guess, so we now have this is the derivative. We then set it equal to 0, and this quantity is also because taking a summation and scrolling back up, we see that that was actually one of the things we were provided. So the summation of x's is actually a red herring. You only need this natural log summation. So plugging that in along with this constant here gets you 996. Setting equal to 0, we get an alpha of 0.5. I feel like a broken record, but whenever you feel like you have the answer to a question, I highly recommend you at least reread the final sentence of the question to make sure that you're not at a middle step in the problem, which is where we're at currently. And that's because the question asked for what is the probability of a claim exceeding 400. It didn't ask you for alpha. So in order to do that, we need to, using the alpha we just calculated, calculate 1 minus the CDF, because we care about it exceeding 400, and then just plug and chug. So that's 1 minus the CDF we're given, where 400 is the x of interest, and then alpha is what we just calculated. That gets us our final solution of 0.706. So now we can scroll up and see that our answer is actually D. Hey, thanks for watching. Again, really appreciate it, and if you enjoy these videos and find them helpful, please consider subscribing, and I'll be sure to keep making this content. Thanks, have a good one.